This computer, okay, now let's do that once more. Come on. So this is the problem. There's too much traffic, it seems. Let's try once again. Okay, good. Okay, so some of you were asking about problem 4 in the exam. Let's discuss that a little bit. So this was so we were given this set. So this is the set of all vectors in R3 such that if you take the dot product, so this was the dot product with this fixed vector, you get 0. So remember that in the first test, we had shown that this sort of sets were subspaces, right? So remember, so recall, let's say. So this was test 1, that for a fixed A, we have shown that this set was a subspace. Right now, this is a particular example. Our A in this case is this vector 1, 1, 1. And now if you rewrite this in terms of dot product, so what is x dot 1, 1, 1? So this is simply, so x1, x2, x3 dot 1, 1, 1. So this will be x1 plus x2 plus x3. So if you rewrite this, the subspace is simply the following. Set of all vectors x1, x2, x3 in R3 such that the coordinates add up to 0, okay? And then carry on. I mean, this is the subspace. Now you figure out what could be a span of this set or this subspace, and then try to show that that particular set is also linearly independent. Okay, so that would be the way to go. So that's a pretty elaborate hint about the problem. So how many of you have been able to figure out this part about translating this subspace into something known like this? Oh, okay, it was the dot product. Okay, exactly. Okay, so let's start today's class. So got that much? Yeah, exactly. So if you get to this point that x1, this is the subspace, then the rest is just finding out a spanning set of this subspace and figuring out that it's linearly independent. That would be a basis. Okay, so find out, find a spanning set for this set and try to show that it's linearly independent. Okay, so that would be a basis. So I can say that much, otherwise I will end up solving the whole problem. Anyway, so let's carry on with today's class. We were doing diagonalization and shown that not every matrix is diagonalizable. Now, the next question is how does one characterize diagonalizable matrices. Okay, so there should be a defining way to identify which matrices are diagonalizable and which ones are not. So let's see the condition. So suppose A is diagonalizable. Okay, so it means that there exists an invertible matrix P and a diagonal matrix D such that we have this relation that D is equal to P inverse AP. P inverse AP. Okay, so that's the relation of being diagonalizable. Now let's investigate this relation a little bit more. We write, let's P in terms of it's the other way, rows of not rows, of a row of column vectors. So let's say P is of this form. So each xi, xi is a column. So this is x1i, x2i, or let's say xj, just to keep parity. So xj to xj up to xnj. So each element in this row is a vector in itself. Okay. So what happens is that now D equals P inverse AP means, so if you multiply with P from the left, what you get is PD equals A times P. Right, and then let's write down what A times P means. So A times P is simply A times x1, A times x2. So this is just matrix multiplication, A times xn. And P times D, so this is x1 up to xn times this diagonal matrix. Right? So this D was a diagonal matrix.
What it is? Oh my God.
So this matrix P times D, and this will give you precisely, if you check the multiplication, so this is lambda 1 x1 up to lambda n xn. Okay, so this is the left hand side. Now PD equals AP, it means that lambda 1 x1 up to lambda n xn, this is equal to A times x1, A times xn. Okay. Someone's mic is on, is it? Someone with is it still on? I don't think so. Seems okay. Yeah, he turned it off. So what does it mean? So what does this, okay. So what does this matrix equation tells you? Any guesses? What page are we on in the eigen3? Let me see. So we are on page 5. So what, yeah, page 5. And what we will do is to sort of cover 4 and 5 also today, because 4 and 5 is mostly examples. So what I plan to do is to cover some of the examples and then leave the rest for you to read so that we can finish off with this chapter today. But for the moment, yeah, we are in page 5. Okay, so without looking at page 5, can you tell me what does this equation says? This particular equation? So this is a matrix equality, right? So what it means is the following, that A times xi equals lambda I xi for each I, one between 1 and n. Agree to that? So this is a matrix equality. So we have this particular matrix equality. So what does it mean? It means that lambda I is an eigenvalue of A. So this is an eigenvalue. Eigenvalue eigenvector equation. So what it means is that this lambda I comma xi is an eigenpair. Okay. Now notice that P is invertible. Since P is invertible, this particular set x1 up to xn, so these are the columns of P. Okay, so this has to be linearly independent. Right? So otherwise, if this set is not linearly independent, then there is a non-trivial linear combination. So these are things which we have done in vector spaces. So there is a non-trivial linear combination among these vectors, and that non-trivial linear combination would give you a non-trivial solution. So it cannot be linearly independent. So being linearly independent means that this set has to be, P being invertible means that this set has to be linearly independent. So what is the upshot? So this is the upshot, is that if A is diagonalizable such that D equals P inverse AP, then D consists of eigenvalues of A, and the columns of P consists of eigenvectors of A such that this set is linearly independent. Could you scroll up? Which point? That's fine, okay. So the key equation is this, that PD equals AP, and from there we conclude that we have this eigenvalue eigenvector equation, and hence we have this upshot for the moment. Okay, so should I carry on? I guess, okay, yeah. Now, what's more is that we have a set consisting of n vectors, which is linearly independent in Rn. So notice that x1 up to xn is a linearly independent set of n vectors in either Rn or Cn, depending on the eigenvalues. So what does this tell you? So you should appeal to one result from linear independence, that in Rn or Cn, let's say, if you have a set consisting of n vectors, so let's write it down. So recall, in Rn or Cn also, if a set of n vectors is linearly independent, then it has to span. So it has to span Rn or Cn. Hence, this set is also a basis. Okay, so this particular set of vectors, the vectors which consist, which forms this matrix P, this set has to be a basis of Rn or Cn. So we say it in the following way, that hence, or maybe in other words, so Rn or Cn, once again, has a basis consisting of eigenvectors of A. So this is an important criterion, in the sense that we can reverse this argument, reverse the above argument. What it means is that if A is a matrix such that its eigenvectors forms a basis of Rn or Cn, once again, depending on the eigenvalues, then A is diagonalizable with P consisting of the eigenvectors as columns and D consists of the eigenvalues. Okay. So what does this mean? So in other words, suppose lambda 1 up to lambda n are eigenvalues of A such that x lambda 1 up to x lambda n forms a basis or Cn, then P consists of this x lambda 1 up to x lambda n, and D consists of this eigenvalues. So you have lambda 1 up to lambda n and zeros elsewhere. Oops. Such that D equals P inverse A times P. Okay, so note, one thing to note is the following, that lambda 1 up to lambda n may not be distinct. Okay, so this is one important thing to note. So we are just counting according to, so we are counting repeated roots as many times as they repeat. So something like if the eigenvalues are 1, 2, and 2, so we are calling 1 to be lambda 1, and the first two we are calling it lambda 2, and the second one to be lambda 3. So overall there are n eigenvalues in that way. So this is one observation, that this eigenvalues may not be distinct. And another observation is that number 2 is that this D and P may not be unique. Okay. For example, if we change, so if we rename, or let's say rearrange the eigenvalues, let's say lambda prime 1, lambda prime 2, lambda prime n, such that lambda prime I is some lambda prime, sorry, not prime, some lambda j, then accordingly we have a new P. So we have a P prime x lambda 1 prime x lambda n prime, and then we have lambda 1 prime up to lambda n prime. So this is our new D. So D prime equals P prime inverse times A times P prime. Okay, so there can be different choices of this diagonal matrix D and P, but the end result is always the same, which is the good point, that you have for any such choice of this diagonal matrix D and this invertible matrix P, you have this relation that D is equal to P inverse A times P. Okay, so any questions up to this point? Is it clear? Okay, I think it is. Okay, good. Well, at least for Cameron, it's clear. So let's summarize a bit. Number one, a square matrix is diagonalizable whenever it is similar to a diagonal matrix. When going from one, can you please still leave about half the previous page on the screen? Okay. Okay, I'll do that. But for the moment, this display is fine. So I'm just showing the summarized part, okay. Number two, a complete set of eigenvectors for A is a set of n linearly independent eigenvectors. Okay, so A is diagonalizable if it has, just to give a name, it has a complete set of eigenvectors. Okay. And of course not, so of course, oops, looks like a smiley. Of course not all matrices have a complete set. Otherwise, every matrix would be diagonalizable. And then in such a scenario, if it is complete, then we know how to diagonalize a matrix. Namely, we form this matrix P out of the eigenvectors. So we form this matrix P out of the eigenvectors and the diagonal matrix out of the eigenvalues, with this eigenvalues being repeated. And we have this relation that D is equal to P inverse A times P. Okay, let's see. Some facts which, or at least one fact which can be used later. So eigenvalues corresponding to distinct, so this is something I mentioned in the last class, distinct come on, not eigenvalues, but eigenvectors. Oh, no, that's fine. Eigenvectors corresponding to distinct eigenvalues are linearly independent. So what does it mean? Suppose we have two eigenvalues, lambda 1 and lambda 2, such that they are not equal. And let's say you have an eigenvector corresponding to lambda 1 and another one corresponding to lambda 2. Then if you consider this set, so this set is linearly independent. And in general, if you have, let's say, x1, x2 up to xk, so k eigenvalues such that they are distinct, and if you form this set x lambda 1, x lambda 2, so corresponding eigenvectors, then this set is linearly independent. Okay, so we take this as a fact, and the idea would be to use it. Okay, so I leave more or less from here. Okay, so how can one use this fact? One obvious corollary would be the following. If A has n distinct eigenvalues, then A is diagonalizable. So proof omitted. I mean, the proof is not really difficult, but it's slightly technical. So we just, one has to use a little bit of induction. So first show that for two eigenvalues, two distinct eigenvalues, this is true. So this particular set is linearly independent. Then assume that the result is true for a general n, and then show this for n plus 1. So that would be the way to go. So maybe I'll just write uses induction. But we will freely use this fact. Okay, so how does one go about doing this or solving this corollary? Can anybody see how it follows from this fact? Any ideas? No ideas? So what does it mean? So A has n distinct eigenvalues. So immediately if you appeal to this fact, what do you get? So let lambda 1, lambda 2, lambda 3 up to lambda n be distinct eigenvalues. Okay, so then how can you use this fact? So collect one eigenvector from each eigenvalue. Okay, so this is a set consisting of n vectors or n eigenvectors. Now, what does this fact tells you? So these are distinct eigenvalues. So then this set is what?
Linearly independent.
I mean, it's just quoting the fact. So this set is linearly independent. So this set is linearly independent. Right? So hence, A has a complete set of eigenvectors, hence is diagonalizable. Okay, so this is an important corollary to note down. So suppose for a matrix you find out that it has distinct eigenvalues and exactly n number of distinct eigenvalues. So n, well, so A is a, keep repeating this n. So A is a n cross n matrix. So suppose you show that it has n distinct eigenvalues, at once you can conclude that it's diagonalizable without actually computing the matrices P and D. D is almost obvious because D consists of this eigenvalues in the diagonal position. So you have your D, the diagonal matrix, but for P, you still need to figure out exactly these eigenvectors. But if you are asked to just show whether A is diagonalizable or not, you can use this type of corollaries or this type of facts. Okay, let's carry on. What do we have next? Some more definitions. Number one, a matrix which is not diagonalizable is called defective. It's a very bad name. I don't like it. I mean, non-diagonalizability might have its own advantages. Why call it a defective matrix? But anyway, just to give a name. Number two, algebraic and geometric multiplicity. Okay. So let A be a, once again, n cross n matrix. Then you know that the characteristic polynomial, it's simply the determinant of A minus lambda I. Now over either real or the complex numbers, this, so you know that this is a minus 1 to the n lambda n plus c1 lambda n minus 1 blah blah cn. So this is a degree n polynomial. So that much you know. Now over generally the complex numbers, not always over the real numbers, you can factorize. So this is lambda minus lambda 1 to the n1, lambda minus lambda 2 to the n2, say lambda minus lambda k to the nk. Okay. Oops. Nk. So this factorization, this over C, not always over the real numbers. Then lambda 1 up to lambda k are the distinct eigenvalues of A, and the positive integers Ni are called the algebraic multiplicity. multiplicities of lambda I. Okay, so these are simply the number of times each eigenvalue repeats itself. That's all it is. So these are called the algebraic multiplicities. Okay, so this ni's. Now let's recall a little bit that E of lambda I, so this is the null space of A minus lambda I, In, is the eigenspace corresponding to lambda I. So this is a subspace, right? So this is a subspace of Rn. So the dimension of E lambda I is called the geometric multiplicity of lambda I. So in the geometric sense, this dimension of E lambda I measures the degrees of freedom that this eigenvalue has. Okay? Because, I mean, dimension measures the degrees of freedom of a vector, or a vector space rather. Okay, so this is the geometric multiplicity, the dimension of each eigenspace. Now, once again, this is a slightly deeper fact. One can show that geometric multiplicity of lambda I is less than or equal to the algebraic multiplicity of lambda I. So this is something one can show, and this is a beautiful connection between the geometric part of an eigenvalue and the algebraic part of an eigenvalue. And so let's call this 1, and number 2, A is diagonalizable if and only if the geometric multiplicity of lambda I equals the algebraic multiplicity of lambda I for each I. Okay, so for each distinct eigenvalue, if the geometric multiplicity and the algebraic multiplicities match, then it amounts to saying that A is diagonalizable, or in other words, A has a complete set of eigenvectors. And how do you get this complete set of eigenvectors? Simply you collect each eigenvectors from this eigenspaces. So what you do, so let's write out. So in case of 2, let Bi be a basis for each E of lambda I, then a complete set of eigenvectors of A is given by just collecting the bases. So B1, B2, up to Bk. Okay, so if you collect this, then this has n eigenvectors. Okay. So any questions about this definition of algebraic and geometric multiplicity? Is it clear? So from time to time, you could switch between showing that A has a complete set of eigenvectors to this thing that the geometric and the algebraic multiplicity, they are the same. Okay, especially this condition that the geometric and the algebraic multiplicity, they have to be same, is useful in showing that a matrix is not diagonalizable. So instead of trying to show that it doesn't have a basis of eigenvectors, what you can do is simply pick up one eigenvalue which you think would work and try to show that for that particular eigenvalue, the geometric multiplicity is strictly less than the algebraic multiplicity. And if you do that, then by number 2, the matrix cannot be diagonalizable. Okay, so this condition is more useful in showing that a matrix is not diagonalizable. Okay, because showing a matrix is diagonalizable is basically trying to extract a basis consisting of eigenvectors. So it would be the same amount of work if you use this condition 1 and 2, or if you exactly try to find a basis of eigenvectors. So it won't make much of a difference. But in order to show that something is not diagonalizable, this is especially useful, this condition. Okay, so let's see. One small remark, and that is something you should note down, that the algebraic and geometric multiplicity depends on the scalars, which means that it depends whether you are working with real numbers or complex numbers. So the diagonalizability, so does the diagonalizability. A matrix can be diagonalizable if your scalars are real number, if your scalars are complex numbers, but it may not be diagonalizable if you are working over real numbers. So let's see an example of that. For the simple reason that any polynomial can be factored over complex numbers, but not over real numbers. So let's say you take an A of this form, 1, 1, minus 1, and 1. Then what is your P lambda? So your P lambda is given by lambda minus 1 square plus 1. Okay. Now, if you want to find the root, so if our scalar is real numbers, then this P lambda has no root. Okay. Oops. Hence, A is not diagonalizable if the scalars are real. Simply because you cannot factor it out. But if we allow complex numbers, then check this, that P lambda is lambda lambda minus 1 plus I times lambda minus 1 minus I. So lambda 1 equals 1 plus I and lambda 2 equals 1 minus I. So these are the two distinct eigenvalues. Okay, and hence by this particular fact, which we did previously, this fact, where is it? Well, let's say using this fact that eigenvectors corresponding to somehow the corollary. Well, at least using this fact that eigenvectors corresponding to distinct eigenvalues are linearly independent, we had this corollary which somehow disappeared now. Oops. That if a matrix has n distinct eigenvalues, then it's diagonalizable. So what happens here is that it's a 2 cross 2 matrix and it has 2 distinct eigenvalues, and hence it's diagonalizable. So if you allow your scalars to be complex numbers, then the matrix is diagonalizable. So if we allow our scalars to be complex numbers, then A is diagonalizable by a previous fact. And what would be the eigenvectors in this case? So the D, you already know, this is 1 plus I, 1 minus I, 0 and 0. So this is our D. To find the P, you need the eigenvectors. So check that E of 1 plus I. So this is the null space of A minus 1 plus I times I2. So this is, let's write down. So A is 1, 1 minus 1, 1. So 1, 1 minus 1 and 1 minus 1 plus I, 0, 0 and 1 plus I. So this is 1. So this is minus I. This is 1. This is this is minus 1. And this is minus I. So this is this is A minus 1 plus I times I2. Okay. Now, how can you row reduce this? So I minus I1 minus 1 times minus I. What you do is add minus I times R1 with R2. Okay. So then you get I1. The first row remains unchanged and the second row is 0, 0. So hence, now you can compute that E of 1 plus I. So this is simply, so what do you have? You have here, so I'm doing things a little bit quickly. So minus x1 times I plus x2 equals 0. So x2 is x1 times I. So this is span of 1 and I. Okay, so this is the span. So this is the eigenspace corresponding to 1 plus I. And now you know that this is simply given by taking the complex conjugate. So 1 and minus I. Okay, and your P is given by writing out this eigenvectors as columns. Okay, so this is your P, and hence you have the following: 1 plus I, 1 minus I equals 1, 1, I and minus I, inverse of that times what is A, 1, 1 minus 1, 1. Okay, so check the details here and check indeed that if you multiply like this, you end up getting this diagonal matrix. So I leave that you to check, leave that for you. So check this step. Also, since we were talking about algebraic and geometric multiplicity, notice here that the algebraic multiplicity of each eigenvalue is 1. And also the geometric multiplicity is 1 because it's just given by the span of one vector. So this is a basis. So this is a basis for E1 plus I. Similarly, this is a basis for E1 minus I. So each eigenspaces has dimension 1. So the geometric and the algebraic multiplicity, they're exactly the same. And we have this diagonalization. So any questions up to this point? This final computation is not done in the lecture note. So this is what I did right now. So maybe there could be some computational mistakes. So check this particular step from finding this eigenspaces up to this multiplication here. Okay, so any questions here? At least how the process is clear, how I went about finding the matrices P and the diagonal matrix. So this is in some sense the first example of diagonalization that we have done. Okay, so if there are no examples, sorry, no questions, then let's carry on a little bit more. So now we have done everything needed to set up the theory, and now let's just move on to examples of diagonalization. Then defective matrices. So what we do is we will see a bunch of problems consisting of diagonalization or non-diagonalizability of matrices and some general problems from eigenvalues and eigenvectors. So we are still in note 10, which is eigen 3. So let's start off with a simple problem. We have seen that this matrix, if you take A to be this matrix 0, 1, 0, 0, 0, 1, and 0, 0, 0. So we know that A is not diagonalizable. By a different method, which we have seen in the last class, right? So we have actually proved. But now let's check what is the algebraic and the geometric multiplicities of the eigenvalue. Now, what is what is the characteristic polynomial? So this is given by A minus lambda I3. But this is fairly simple in this case. So this is, well, this is minus lambda 1, 0, then 0 minus lambda 1, and 0, 0 minus lambda. So this is just minus lambda cube. So this is the characteristic polynomial. Okay. Hence, lambda equals 0 is the only eigenvalue. So this is the only eigenvalue. And what is the algebraic multiplicity of it? Anybody with algebraic multiplicity of what?
3.
So what is the algebraic multiplicity? Yes, okay, 3. Now let's figure out E of 0. So E of 0 is simply the null space of A. So this is the null space of this matrix. And you don't even need to row reduce it. So this is 0, 1, 0, 0, 0, 1, 0, 0, 0 times x1, x2, and x3 equals this vector 0, which means, so from the first equation, you have x2 equals 0, and from the second row, you have x3 equals 0. And x1 is the only free variable. So E0 is given by, well, not definition, but just equality. So this is given by span of 1, 0, 0. Okay, since anything is of this shape, right? x1, 0, 0. So this is x1 times 1, 0, 0. So it's just span of this. So the dimension of E0 is 1. Hence, the geometric multiplicity of 0 is less than the algebraic multiplicity of 0. Okay, the algebraic multiplicity is 3 and the geometric multiplicity is 1. So that's another reason why this is not diagonalizable using whatever theory we have set up. I mean, for general matrices, you cannot use such reductio ad absurdum kind of arguments, which we did for A, but you can always use this type of arguments to show that the geometric and the algebraic multiplicities, they do not match. Okay, so hence A is not diagonalizable, okay, which we already know, let's say. Okay. Another way, since we are in this problem, another way to show that lambda equals 0 is the only eigenvalue is the following. So another, let's do this here. So another way to show that lambda equals to 0 is the only eigenvalue. So recall that we have this property that a cube is 0, right? So a cube is given by the 0 matrix. Then any equation, not any, but let ax equals lambda x be an eigenvalue, eigenvector equation. So this vector is not 0. Okay. Now what we can do is the following. So we have ax equals lambda x. So we multiply with a on both sides. Okay. So then a square of x equals a times lambda x. Okay. Now lambda being a scalar, so this is simply lambda times ax. The scalar comes out. Now ax once again is lambda x, so this is lambda times lambda x. So this is lambda square x. Now multiply with a once again from the left on both sides. Okay. On the left hand side you have a cube times x. On the right hand side you can similarly bring out lambda square since this is a scalar. So this is lambda square times ax. And once again ax is lambda x. So this is lambda square times lambda x equals lambda cube times x. Okay, but a cube being 0, it means that the left hand side is completely the 0 vector. Okay, and on the right hand side we have lambda cube times a vector which is non-zero. So this x is non-zero. So the only conclusion that we can have from here is that this lambda cube has to be 0, hence lambda equals 0. So this is another way to show that lambda equals 0 is the only eigenvalue for this matrix. And this is not just restricted to a cube equals 0. So let's say for any natural number n you have, so let's write it here, we can use this method or this trick to show that lambda equals 0 is the only eigenvalue for a matrix A such that a to the n equals 0 for some n greater than or equal to 1. So we can use the same trick. So instead of lambda cube, here you will have lambda to the n equals 0 and hence lambda equals 0. But the process remains the same. Okay, so I think this is a good point to stop here. We weren't able to cover what I thought I would. So what I do next week on Tuesday, we do some problems from eigen 4 and eigen 5. Okay, so eigen 4 and eigen 5 consists of only problems about eigenvalues, eigenvectors, and diagonalization. So we do some of the problems, and hopefully on Tuesday we can switch to vector calculus. So that would be the idea. So that's it for the day. Any questions about the last part, about this formal proof? Or any other questions? By the way, I have increased the submission time, or I switched the submission time to 7 p.m. So you have a little less than 2 hours to submit. So you still have time to submit, so it won't be late. Where can we find the recorded lecture? So usually I post the YouTube link on eCampus. So I just post the link on eCampus. I record the lectures on YouTube and send the links. So that's what I've been doing. Yes, the most recent submission will be graded, exactly, yeah. So you can upload as many number of times you want until you are satisfied or exhausted, maybe, whichever comes earlier. But yeah, so the most recent submission will be graded. Anything else? So it seems like most of you are still engaged with the exam, maybe. So if not, then I will say goodbye and have a nice weekend and stay safe. Enjoy at home. Yeah, you too. Stay safe and wash your hands. Bye-bye. Bye.